Tiani, and this is my Physics 2212 Lab 4. Okay, so first we're going to start with the purpose. The purpose of this lab is to observe and determine how a bar magnet can induce a magnetic force on a conducting tube. We're going to apply Newton's third law to understand the fundamentals of the experiment, and we're going to model magnet and tube interactions computationally and then compare the theoretical results from the computational model with the experimental results. So a sneak peek at the findings: the average fall time found by the trials of the experiment came out to be 1.29 seconds, and then the computational model predicted fall time came out to be 0.943 seconds. So as you can tell, they're very similar. These are the main models and physics fundamentals used in this lab. So first we have Faraday's law, which the equation for that is shown right here, which we use to find the EMF. Then we have the Biot-Savart law. Lenz's law is that the magnetic field from the induced current will point in the opposite direction of the change in flux to restore original conditions. And then we have Ohm's law, which is I equals V over R, and then I being the current through the conductor, V being the voltage, and R being resistance. And then the magnetic field of a bar magnet, which we're going to use Newton's third law to explain why the force from the loop on the bar magnet is equal and opposite the force from the bar magnet on the loop. The assumptions in this lab are that the only forces acting upon the magnet are magnetic and gravity, and that air resistance is negligible. The bar magnet is the magnetic dipole, and then we're going to ignore Earth's magnetic field. The system of this experiment is the aluminum foil and the magnet, and then the surroundings is everything else. The initial conditions are that there is zero magnetic force and the magnet has not been dropped in the tub yet. So here is the data gotten from the trials of the lab. So as you can tell, I wrote a start time and an end time to show, and then the average came out to be 1.29 seconds of the 5 trials. So the procedure was that we first determined the magnet's north pole. Then you must take measurements of the roll of aluminum foil. Then drop the magnet through the roll and record on video and repeat the step 6 times for 6 trials. And then using the tracker app, determine the precise time for the magnet to fall. And lastly, we're going to create a computational model to simulate the experiment and get theoretical data to compare with the experimental data. So the first part of the coding is shown here. So here we just initialize the values of the tube, the length, width, inner radius, and the full radius. And then here we initialize the values of the magnet, the mass and the magnitude of the magnetic dipole. And then this function right here creates the magnetic field based on the formulas from the physics fundamentals slide. This is the calculation for it. And then this slide shows, so this snippet of the code shows the function that was used to calculate the magnetic flux using the formulas from the physics fundamental slide. This line right here is the calculation for the gravitational force, and then finally you put it all together here to calculate the magnetic force as shown as in this line, the net force, and then velocity and position in these last 2 lines. So this is the results we got on GlowScript. So the screenshot shows that the current is moving downward with the falling magnet. And then this graph has a negative slope because the force of gravity was stronger than the magnetic force. And then the slope flattens out to 0 because the magnet experiences constant velocity since the force is summed to 0. So data versus model predictions. The experimental values and theoretical values were similar, meaning that there were few sources of error in the experiment, and most assumptions did not make a large impact on the overall results of the experiment since the computational model represents an ideal scenario. Some possible sources of error could include that the bar magnet was assumed to be a magnetic dipole, or that air resistance was assumed to be negligible, or that a slight magnetic field of the aluminum foil may be present, or there could just be human error in time measurement with the stopwatch. And here's the what if questions. So what if the resistivity of the conductor was reduced close to 0? So if this happened, the magnet would not fall through the tube at all because the breaking point will increase, so it balances out the gravitational force. And then what if holes were cut into the tube? The normal current flow through the ring currents would be disrupted, and because less current is flowing through the tube, the breaking force would then in turn be weaker.